Okay, so I record it now. So I would like to ask the first speaker to start.
Yes, I start.
So can you please share your slides, or do we have a pre-recorded? Okay.
Hello and welcome to this talk on timed games with window parity objectives. I am James Main and this is joint work with Michael Rondour and Jeremy Sproston. In this talk I will cover window parity objectives in a timed setting and will discuss two objectives. For a given bound lambda on the size of windows, the direct timed window parity objective requires that at all times along the play, we see a window in which less than lambda time unit elapse and in which the smallest priority that appears in the window is even. The timed window parity objective requires a direct objective to hold from some point on and is a prefix-independent variant of the direct objective. We will discuss both verification of timed automata and realizability in timed games for timed window parity objectives. Each of these problems can be solved by a reduction to the same problem for safety objectives in the direct case and Kobuki objectives in the non-direct case. I'll open this talk by presenting the models we have used, starting with timed automata. Timed automata are used to model real-time systems. The elapse of time in timed automata is measured by a finite number of clocks that all progress at the same rate. Clock constraints are conditions appearing in timed automata and are conjunctions formed by inequalities comparing a clock to a constant natural number. Here we can see an illustration of a timed automaton, and timed automata consist of a finite set of locations, each constrained by an invariant with a distinguished initial location. So here the initial location is indicated by an incoming arrow and is location L0. And we also have a finite set of edges, each labeled by a guard, an action, and set of clock to reset. So for instance, the edge from L1 to L2 has the guard x greater than 3, uses action A, and resets clock x. We will always assume that there is a clock gamma in all timed automata that cannot be reset. Timed automata give rise to uncountable transition systems in which the states are pairs of locations and clock valuations, so mappings that assign a non-negative real number to each clock. The initial state of this transition system will be formed by the initial location of the automaton and a clock valuation that assigns 0 to each clock. Moves of this transition system will be pairs DA, where D is a delay, and A is an action, and it means wait for D time units, then use action A. We also allow not to use an action of the automaton, but instead just waiting, so that is waiting for D time units to elapse without taking an edge. The transitions that are available in this transition system will be constrained by the invariants and guards of the timed automaton, and we will define a path to be an infinite sequence of states and moves that follow transitions available in the transition system. So for the problem of verification in timed automata, we are given a specification as an objective, which we will consider to be a set of correct sequences of states, and we will want to check that sequences of states that are derived from paths of the timed automaton comply with the objective. However, in timed automata, not all paths are meaningful, and we will ignore what we call time-convergent paths. A time-convergent path is a path along which the valuation of the global clock is bounded. In other words, it is a path, an infinite path, in which a finite amount of time elapses. Paths that are not time-convergent will be referred to as time-divergent. So the verification problem is stated as follows. Given an objective, we have to check whether all time-divergent initial paths of a timed automaton comply with the objective. Now I'll move on to timed games. We will consider two-player games that are played on timed automata. A timed game will be given by a timed automaton and a partition of the actions into player 1 actions and player 2 actions. The games we are considering here are concurrent. Each round proceeds with having both players present a move, and then the play proceeds following a fastest move. If both players suggest moves with the same delay, then the play progresses by choosing one of the two moves non-deterministically. So for instance here, I have depicted a timed game in which the actions of player 1 are A1, the actions of player 2 are A2. If player 1 from the initial location and with all clocks evaluating to 0 plays moves 1 A1 and player 2 1 A2, there are two possible starts to continuations to this play. Either we move to location L1 by following player 2's transition, but we also can move to location L2 by following player 1's move. The plays we consider here are non-terminating, so plays will be infinite sequences of states, then pairs of moves, one of player 2, one of player 1, and so on and so forth. And we will define a strategy as a function that maps a finite prefix of a play that ends in a state to a move of the player whose strategy it is. Winning in time games is defined in a way that takes into account time convergence. So we will distinguish objectives from winning conditions. Given an objective, we will say that a play belongs to its associated winning condition if one of the two following conditions is fulfilled. Either the play is time divergent and satisfies the objective, and if the play is time convergent, we will want it to be so that from some point on, transitions in the play cannot be achieved by player 1's moves. Therefore, the convergence is attributed to player 2 and player 1 is not responsible for the convergence. Thus, we will say a strategy is winning from some initial state if all plays that start in this state that are consistent with the strategy satisfy the winning condition rather than the objective. This gives the following formulation of the realizability problem that requires, given an objective, to check whether player 1 has a winning strategy from the initial state. Besides the timed window objectives we will later be introducing, we also consider the following untimed classical objectives. The safety objective requires, for a given set of locations f, that we never visit locations in f. The Kubuki objective, also defined by a set of locations, requires that we visit these locations finitely often. The Parity objective, defined by a priority function that assigns to each location a non-negative integer, requires that the smallest priority we see infinitely often is even. For this classical parity objective, there are no timing constraints between odd priorities and smaller even priorities. We can construct a path in the automaton depicted here such that the delay between 1 and 0, that is smaller even priority, is increasingly larger as the play goes on. To do this, it suffices to simply loop through the automaton, waiting increasingly longer in location L1 each time it is visited. So 1 time unit the first time before taking the edge, 2 time units the second time, 3 the third, and so on and so forth. Thus, as long as the path advances, there's a greater delay between 1 and 0. By using the window mechanism, we can specify timing constraints between odd priorities and smaller even priorities. The window objectives are based on the notion of good windows. So if we fix a bound lambda on the time of windows, a good window for the parity objective is a window in which strictly less than lambda time units elapse, and the smallest priority that appears in the window is even. Let us consider this timed automaton and a window size of at most 2. We can give an example of a good window and a bad window. So if we start in location L0, the only priority in the window will be that of L0, so 1. This is an odd priority, so we do not yet have a good window. If we move after 1 time unit to location L1, now 1 and 2 both occur in the window, but the smallest priority being still odd, we do not yet have a good window. If after a delay of 0 now we move to location L2, 0 now occurs in the window, hence the smallest priority of the window is even, and furthermore only 1 time unit has elapsed, so we have a good window at the start of this path. Now, if we do a similar path, but instead of moving directly from L1 to L2, we wait 1.2 time units, in this case, the point in time at which the smallest priority of the window is even is later than 2. Thus, we have a bad window at the start of this play. Formally, the good windows, we use them to define the timed good window objective that expresses that the window at the start of the play or the path is good. And formally, we require from a sequence of states that there is a point at which the smallest priority that appears from the start is even, and that the total time elapsed from the start is less than lambda at the point in time at which the smallest priority is even. We say that the window opened at some step j closes at step n if n is the first point in time at which the smallest priority of the window is even. Thus, we will require that the smallest priority between steps j and n is even, and that for any previous step n prime prior to n, the smallest priority between steps j and n prime must be odd. This also implies that it is the priority of n that is of ln that is the minimum between steps j and n. If a window does not close in strictly less than lambda time units, we will say that this window is bad by opposition to good windows. From the time good window objective, we can define the direct time window parity objective that requires that there is a good window at all steps. So formally, we simply require that all suffixes of a sequence of states satisfy the time good window objective. This discrete objective, let's say, is equivalent to requiring good windows even in intermediate states that occur during delays. So, for instance, if we know that the window opened at step Lj closes at step Ln, we can also deduce from this that any window opened in the delay between steps Lj and Lj plus 1 will also close at step n, for the first reason being that we see the same priorities in these two windows, and that if the window opened in step j closes in less than lambda time units strictly, then the window opened during the delay, because it is smaller, will also contain less than lambda time units. From the direct time window parity objective, we can define the time window parity objective that requires the direct objective to hold from some point on. And thus, formally we will define it as the set of sequences of states that have a suffix that satisfy the direct objective. The key to our algorithms is the inductive property of windows. Along all paths of a timed automaton, at any step j, if the window we open at step j closes at a step n in strictly less than lambda time units, then for all steps between j and n, we can infer that the window opened at that step is good. Intuitively, what happens is that if we open a window at step j and close it at step n, then necessarily the smallest priority between steps j and n will be that of location ln. Thus, if we open a window later down the line, say at some step j prime, when we reach n, the minimum between positions j prime and position n will be the priority of ln, and thus the window will have to have been closed by that point in time, given that less than lambda time units elapse. Thanks to the inductive property, we know that we can then just keep track of one window at a time to check whether a window parity objective holds or not. And thus we can reduce the verification and realizability problems for the direct time window parity objective to the verification and realizability problems for the safety objective, where we will encode in our safety objective to see no bad windows. And for the non-direct time window parity objective, we can proceed similarly, except that we will consider a Kobuki objective that will require that we see bad windows finitely often along a play or a path. In our reduction, we expand timed automata so that it includes information on the current window in order to detect bad windows. We expand locations to encode the current lowest priority of the window, or alternately a special value bad that indicates a bad window was detected. To measure the size of the window, we use a new clock z that was not present in the original timed automaton, and we change guards and invariants in a way that ensures bad locations are visited whenever a bad location is witnessed along a time-divergent path. To interact with the locations labeled by bads, so bad locations, we will introduce two new actions, beta 1 and beta 2, which we will summarize with beta in the upcoming example. When we are given a timed automaton such as the one above, we can construct the expansion as follows. So, as for the initial state, it is the state obtained by, for the initial location, we consider the location obtained by the initial location of the original game, and its priority, given that when we open a window in a location, the only priority in this window is that of the location. Hence, we start in location L01. Given that 1 is odd, this means this window is open, and thus we must take care in case it becomes a bad window. To this end, we prevent the passage of time beyond the detection of a bad window, prevent any outgoing transitions if a bad window is detected, except transitions that are directed to a bad location. When moving to a bad location, we reset clock Z so that when we exit the bad location, we reopen a new window in the current location. So for instance, if a bad location is detected in location L0, when we exit location L0 bad, we will reopen a window in location L0 and its only priority will be that of L0, so 1. So we move back here. When we move from a location that represents a window that is still open to another location, we must update the current lowest priority of the window. So if we move from location L0 to location L1 following this edge, then in the expanded game, we must move from location L01 to L1, and then we determine the current smallest priority of the window by comparing 1 to the priority of L1, so 2. Given that 1 is smaller than 2, we go to location L11. That is a not location that behaves similarly to L01. When we move from L11 and enter L2, in this case, we enter a location of priority 0, so the smallest priority is updated to 0, and the window closes. We have a good window. When we are in a location labeled by an even number, then all windows are closed and there is no need to take care of bad windows anymore. Furthermore, when we exit such a location, we reopen a window in the target location. So if we exit location L2 to go to location L1, and we leave L2 0, what we do is we reset Z so as to measure the size of the new window, and we set as the current lowest priority of the window that of the location we are entering, in this case L0, so 1. And this summarizes our reduction. To prove its correctness, we can use two mappings, an expansion mapping and a projection mapping, where the expansion mapping will map paths or plays of a timed game or timed automaton to those of its expansion, and the projection mapping works in the other direction and takes the paths or plays of an expanded timed automaton or game and yields paths or plays of the original timed automaton and game. We can construct these two mappings so that they behave well with regard to our objective. So, for instance, we can have the following property that for all time divergent paths or plays, the play will satisfy the direct time window parity objective if and only if its expansion satisfies the safety objective in the expanded game. For the projection mapping, we have an analogous property where we have for all time divergent initial paths or plays of an expanded timed automaton or game, if it satisfies the safety objective in the expansion, it is equivalent to having its projection satisfy the direct time window parity objective in the base game. And we have similar results with the non-direct objective and Kobuki objective on the other side. This yields the following theorem that all time divergent initial paths of a timed automaton will satisfy a direct timed window parity objective if and only if all time divergent initial paths of its expansion satisfy a safety objective over bad locations. Similarly, we have the same property with the non-direct timed window parity objective and a Kobuki objective on the expansion. We can also use the two mappings, expansion and projection, to translate winning strategies between a timed game and its expansion. The expansion mapping can be used to derive from strategies of the expanded game a strategy of the base game by composing the strategy of the expanded game with the expansion mapping and replacing any actions beta by simply standby actions. And for the projection mapping, we have a similar construction where we compose it with a strategy, and in this case we must take care of reinforced invariants that require visits to bad locations. It follows from these translations that we have a winning strategy for player 1 for the direct time window parity objective from the initial state of a game if and only if there is a winning strategy for player 1 or the safety objective in the expanded game from its initial state. And similarly, we have a winning strategy for the time window parity objective from the initial state of a game, if and only if there is a winning strategy for player 1 for the Kobuki objective in the expanded game. We can also use our reduction to handle multidimensional objectives, that is, conjunctions of direct time window parity objectives or conjunctions of time window parity objectives. The inductive property ensures that we need only keep track of one window per dimension, thus we can do an analogous construction where we expand locations with vectors of priorities and add one new clock per objective so as to handle multiple dimensions. Our reduction yields a p-space algorithm for the verification problem and a next-time algorithm for the realizability problem, even in the case of multiple dimensions, even though for verification, we need to check one dimension at a time to obtain a p-space algorithm. To establish hardness, we can reduce verification and realizability problems for safety objectives to verification and realizability problems for direct or non-direct time window parity objectives, simply by expanding automata so that once the safety objective is violated, windows can no longer close, and otherwise windows always close immediately prior to the safety objective being violated. If we compare the complexity of the multiple dimensional case for timed games and untimed games, one can notice that we have the same complexity class. So in other words, dense time comes for free for timed games with multiple window parity objectives. Thank you for listening to my talk.
So thanks a lot for the talk. So we have a time for a short Q&A session. So are there any questions? So for the moment, I do not see. So by Danielle, so please speak up.
Yeah, so I have the privilege of being able to speak up alone. Yeah, so the technical result is quite interesting, and the reduction, I like that, and the talk. But now, suppose I am Banged Olufsen. I bought the license of Upal in 97, and now you have to convince me to buy the upgrade of Upal with your feature. So why should I buy? So basically, what are the specifications that some industry can hope to satisfy using your formalism?
So the window mechanism that we use is actually useful to specify timing constraints between priorities, as I explained in the talk. And so now I believe that I'm not familiar with the functioning of Upal itself, but I'm not sure that you can have properties where you require a phenomenon to happen. Say you want a certain property to be verified in under a certain amount of time, but regularly, or maybe it allows it. Sorry, I can't answer the question.
Okay, forget about Upal, but so would you say your result is more about say theoretical specification about timed languages, or it is more about, so who are the buyers of your tool?
It's really the interest of the result lies in the fact that we can actually bound the time required. So you can see, say, a null priority as a request and an even priority as a response, and our result allows actually to bound the time between requests and responses in this way.
Okay. Any other question? But if not, then I have a sort of related question. So, so I wonder whether these window objectives correspond to some natural class of temporal properties specifiable in some suitable temporal logic. So have you investigated this relationship between your objectives and some, specification mechanisms?
As of now, that we have not yet investigated any such relationships, so I cannot expand upon your question. Sorry.
Okay, good. Anything else? So I do not see any hands, right? So thanks a lot for being with us. And I guess we can go on with the next talk. So I think the virtual presenter is Pierre. I guess we also have a pre-recorded presentation. So can you please start it? Yes, okay.
Hello everyone, I'm going to present a work called Arena-Independent Finite Memory Determinacy in Stochastic Games, which is published at ConcurA 2021. This is joint work with Patricia Bouillet, Youssouf Walaj, Michael Randour, and I am Pierre van den Heu. So first of all, I'll give a brief outline of my talk. What we want to do is to automatically design optimal controllers for systems that have to interact with an antagonistic and stochastic environment. We assume that the system has some objective or specification that it wants to satisfy. And we want to build a controller that do that as well as possible, that is an optimal controller. We can model that as a game between the system, which is a player, and its antagonistic environment. And so we can rephrase this question using a game theoretic vocabulary as the strategy synthesis problem for zero-sum stochastic games. And here we'll assume that all games are turn-based. The main question we seek to answer is for which objectives are simple controllers sufficient to be optimal? And here we'll assume that simple means that it can be implemented with finite memory. So the question is the finite memory determinacy question, which is for which objectives do finite memory controllers suffice to be optimal or to play optimally using a game theoretic vocabulary? This article is a follow-up to a ConcurA 2020 paper, which dealt about deterministic games, and here we've generalized it to stochastic games, and we've also given more results and insight about the problem. Here's the plan of the presentation. I'll first introduce the model of stochastic games. Then I'll explain the words from the title, which is Arena-Independent Finite Memory Determinacy. That's a stronger property than finite memory determinacy, but one for which we can say quite a few things. And that's what I'll do in the last section, in which I'll list our contributions, which are 3 characterizations of that property. Let's start with stochastic games. So a stochastic game is the given of some kind of finite graph, which would be called an arena. This graph has its state space split into 2. There will be states that are controlled by player 1, which are depicted by circles, and states that are controlled by player 2, which are depicted by squares. In every state, the players have some available actions, that is, transitions that they may take from that state. And as we are in stochastic games, these transitions may happen probabilistically. So for instance, in this state, if player 1 chooses the leftward transition, then with priority 1/2 we stay in the same state, and with priority 1/2 we go to the other state. And the game happens for an infinite duration. We assume that there is some token in a state, and the player who controls that state may choose where to send the token next, for instance here, and then the player who controls the new state may choose where to send the token next, and so on for an infinite duration. In order to specify objectives, we will label transitions with colors. So here there are 3 colors, A, B, and C. And in order to describe how the players play, they may define a strategy, which is a function that describes for each possible sequence of transitions what the player wants to do. So if we consider a strategy for player I, it will be a function that takes as an input a sequence of transitions that end in a state controlled by that player. And in stochastic games, it makes sense to consider in general strategies that are randomized. That is, they may choose to take distribution over action as a choice. And so when both players have fixed their strategy, an object that is generated is a distribution over infinite sequences of colors. So the token moves for an infinite duration, so that defines an infinite sequence of colors. But there are 2 sources for randomness, with one in the arenas and one in the strategies. And so the generated object is a distribution over the infinite sequences of colors. And one general way to define an objective for both players is as a total preorder over the distributions over infinite sequences of colors. And here we'll consider that all games are zero-sum. That is, the objective of player 2 is the exact opposite of the objective of player 1. So if player 1 wants to get the best possible outcome for that pre-order, player 2 wants to get the worst possible outcome for that pre-order. So the main question is, given an objective, how simple can optimal strategies be? And in stochastic games, there are commonly two measures for strategy complexity. There is how much randomization the strategies need to use, and how much memory, that is, how much information must be remembered as the game happens. So let us consider a small example. Here we assume that player 1 wants to maximize the probability to see both A and B infinitely often. And in this arena, player 1 can actually guarantee that with probability 1, both A and B will be seen infinitely often. So we could actually call this objective Buki A and Buki B to use a name from the literature. And there are two natural ways to do that. So one way could be in this state for player 1 to take the rightward transition with probability 1/2 and the leftward transition with probability 1/2. And so this will guarantee that with probability 1, both B and A will be seen infinitely often. So maybe B will be seen more often, but that's fine. You just want to see both infinitely often. So that strategy would be randomized because you need to play something with some probability and some other thing with some probability. But you don't need memory because you always do the same thing in the same state. Another way to win would be to use memory but no randomization. So you might start by taking that transition to see B, and then you try to go leftward until you see A. And when that's done, you see B again, and so on. So in that case, you need to change your behavior in that state. When you've seen B, you want to go see A, and when you've just seen A, you want to see B. But you do not use randomization. And in that case, what you need to remember is the last color you've seen. Was it B or was it A? And here, so you can use either randomization or memory to win. One or the other is sufficient, but you need to use one of these. So that was a small example. And in this work, actually, we would like to consider strategies that use finite memory, but that are also pure. That is, that they do not use randomization. So I will now formalize what is a finite memory, and I will explain the exact setting in which we are able to obtain a result, which is the arena-independent setting. We can actually compose a finite memory strategy as two things, a memory structure and a next action function. So memory structure is roughly an automaton with no finite state. So even a deterministic automaton, it has a finite set of states, one initial state, and an update function that updates the memory when a color is seen, a deterministic update function. Here is one example. So this memory structure could be used to play optimally in the previous arena for the objective Buki A and Buki B, because it actually remembers what is the last color that you've seen. So if you're in M1, you know that the last color that you've seen was A because you've just tried A. And when you're in M2, you know that the last color that you've seen was B. So this describes the memory that you need to use, but it does not implement the strategy yet. You still need to decide what you want to do in every arena state and every memory state. So that is given by a next action function. So once you consider an arena, you can actually define a function that takes an input a pair arena state and memory state, and that returns next action to follow. So as I've said that here we would consider pure strategies, that is, strategies that do not use randomization. I just write A here and not distributions over A. So you can notice that it's perfectly possible to define memory structure without considering an arena, but that's not possible when you want to actually implement the strategy. And so this actually brings us to a distinction between two kinds of finite memory determinacy. So in the Buki A and Buki B example, the memory structure I've shown that remembers what is the last color that has been seen between A or B. So it was sufficient for the arena that I've shown, the small arena, but it's actually sufficient to play optimally for all arenas for player 1. And so for this particular objective Buki and Buki B, we can state a strong property, which is that there exists a single memory structure, this one, that suffices to play optimally in all arenas. So now let us consider a second case, which is a bit artificial, but I hope it's easy to understand. So we will consider this class of arenas for player 1. which depend on a parameter n here that describes the number of states before reaching this state. And we assume that the objective of player 1 is, after seeing all the ones here, player 1 will consider the sum of all the ones and wants to bring it back to 0 in Sn by taking sufficiently many minus ones, and then when it's exactly 0 to go rightward in this final state. And to do that, player 1 needs to take that edge n minus 1 times and then go to that state. And it's not possible to do that by using less than n memory states. And so n memory states are both necessary and sufficient to win in every of these arenas for player 1. So in this case, what we can notice is that it's actually always possible for all arenas from this class to win with finite memory, but it's not possible to just always take the same finite memory structure. You need to first look at the arena and then pick a finite memory structure that will be sufficient to win. So what we can say is that for this objective in this class of arenas, for every arena in this class, there exists a finite memory structure. So that's a weaker property than the first one, because you can just define one single memory structure that suffices for all arenas. And that's why in this case, we talk about arena-independent finite memory, and that's the case we are interested in the first case here. A key observation in our work is that for many objectives from the literature, actually, pure arena-independent finite memory strategies suffice to play optimally. And I'll give here a few examples. So the first kind of examples are objectives for which pure memoryless strategies actually suffice. So memoryless strategies are simply strategies that do not remember anything about the past and that make their decisions just by looking at the current arena state. And they are a specific case of arena-independent finite memory strategies, since they can be implemented with the same trivial memory structures that just has a single state. And so examples are given by objectives that consist of maximizing the probability of reachability, Buki or Parity objectives, or for instance, maximizing the expected value of the discounted sum function, and so on. Another interesting class of examples are given by omega regular objectives. And the idea is that omega regular objectives are recognizable by a deterministic parity automaton that you can use as a memory structure. And that suffices, since parity objectives are memoryless determined. So examples are given by all kinds of Müller objectives or the generalized parity objectives. A recent and interesting example is given by lexicographic reachability safety objectives, which is an objective very specific to stochastic games, in which you want to visit or avoid certain targets with some preferences between targets. And here, the memory actually depends on the number of targets, but that's fine, since you can fix the number of targets before looking at arenas. So given a fixed number of targets, you can find a memory structure that suffices, no matter how large arenas using these targets are. And unfortunately, there are also examples in which finite memory strategies suffice. So we can talk about finite memory determinacy, but not in an arena-independent way. So you have to first look at the arena before you can choose a sufficient memory structure. And an example is given by a variant of energy parity games in stochastic games. I will now state our contributions, which are three characterizations of arena-independent finite memory determinacy. And the first one is what we could call a 1 to 2 player lift. So the idea is that we will reduce the problem of memory sufficiency in 2-player games to the same problem, but just in 1-player games. And so a 1-player arena, 1-player stochastic arena of some player, is simply an arena in which that player controls all the states. And the hypothesis is about the sufficiency of a single memory structure, which can be different for player 1 and player 2, so M1 for player 1 and M2 for player 2. And the hypotheses say that these memory structures are sufficient for these players to play optimally in all their own one-player arenas with pure strategies. And you may be more used to the terminology of Markov decision processes for one-player stochastic arenas. And with that, it tells you that in all 2-player stochastic arenas, you can actually also play with the same fixed memory structure, which is given by the product of M1 and M2, so which you can see as a direct product of automata, and also using no randomization. So the gist of that result is that it reduces the sufficiency of pure arena-independent finite memory strategies in two-player zero-sum games to the same problem in one-player games. And one-player games are easier to study since you don't have to consider all the possible behaviors of the other player to prove things. It's just basically a graph with stochastic transition in which you want to prove some memory result. So it's not at all the first time that such a 1 to 2 player lift has been stated. This has been done already in other more restricted contexts. So the first one was about finite deterministic arenas under memoryless strategies, which has been stated by Jambert and Zielonka in 2005. So that is, if you want to prove that memoryless strategies suffice in two-player games, you just have to prove it. In two-player deterministic games, you just have to prove it for one-player deterministic games. And this has been extended in two orthogonal directions later. So first of all, in finite stochastic arenas, so with pure memoryless strategies in 2009, also by Jambert and Zielonka. And last year at ConcurA for finite deterministic arenas, but with a larger class of strategies, which are arena-independent finite memory strategies. And so this year we have been able to combine both extensions into one to show a 1 to 2 player lift for finite stochastic arenas with the larger class of strategies of arena-independent finite memory strategies with no randomization. And to be absolutely complete, I will mention two other 1 to 2 player lifts. So one of them is a very recent preprint that extends the results from ConcurA last year about deterministic games to a slightly larger class of strategies, of the class of mildly growing strategies. So it doesn't cover many more examples from the literature, but it's a very interesting generalization that pushes the technique up to its maximum. And there is also another example with a very different technique about infinite deterministic arenas, but with memoryless strategies that is based on characterization of parity games by Kolkomba and Nowinski in 2006, and that the 1 to 2 player lift has been discussed a bit later by Kopczynski. Okay, so now we know how to reduce this problem about 2-player games to the same problem about 1-player games. However, it might still be difficult to prove the memory sufficiency of some memory structure in all 1-player stochastic arenas, in all Markov decision processes. And so we provide a characterization for the 1-player arenas. We consider a slightly restricted class of objectives. We consider objectives that can be expressed as a payoff function, that it takes an input, an infinite sequence of colors, and that returns a real number. And so the objective of player 1 is to maximize the expected value of that payoff function. And so we say that a memory structure M suffices to play optimally with pure strategies in all 1-player stochastic arenas of player 1, let's say, if and only if. And then we consider two properties of the objective, if and only if the objective is both M monotone and M selective. And here I'll explain M monotony, and I will leave M selectivity aside for simplicity. So given a memory structure M, there is a natural equivalence relation we can define on the finite sequences of colors, so on the finite words on the alphabet colors, on the alphabet C. So given two finite words, we say that they are equivalent with respect to the memory structure simply if they reach the same state of the memory structure when they are read from the initial state. So it's a deterministic automaton, basically, so it's well defined. And the property that we want to check is that for any pair of arenas, A1 and A2, if you take two words that are equivalent, here W and W prime, so let us focus on the drawing, then you don't need to use both A1 and A2 to play optimally after W and W prime. One of these arenas, either A1 or A2, is at least as good as the other to play, no matter whether you start here or there. And so there needs to be some consistency after the prefixes, after the finite words. You can't need to use both arenas. And so this property must be true for all pair of arenas and for all pair of worlds that are equivalent with respect to the memory structure. And so that's monotony. And selectivity is a similar kind of idea, but this time not about prefixes, but about cycles. So it's also possible to classify cycles given the memory structure M. And then we want to show that for any pair of arenas, given some properties of cycles there and of prefixes here, but of one of these arenas is always sufficient to play optimally. This characterization was known in deterministic games, so both for memoryless and arena-independent finite memory strategies, but not in stochastic games. And the proof in stochastic games is actually quite more involved than the proof for deterministic games. And we were helped by a third characterization of arena-independent finite memory strategies, which I won't spend too much time on since it's quite technical, but basically, if a memory structure M suffices to play optimally with no randomization, then M also suffices to play subgame perfectly, which is a stronger property than optimality. So subgame perfection tells you that a strategy is not only optimal from the initial state, but after any prefix that you could find in the arena hierarchy. But I won't spend more time on this. So let us briefly conclude. Our contributions, I would say, is to further the understanding of arena-independent finite memory determinacy, this time in stochastic games, thanks to characterizations of arena-independent finite memory determinacy. For future work, there are two reasonable extensions that we would like to investigate. So the first one is whether it's possible to obtain a similar kind of results for infinite arenas. And the second one is about the arena-dependent case, that is objectives for which finite memory suffices to play optimally, but not in an arena-independent way. So we would also like to investigate that case more. Thank you very much for your attention, and I will gladly take your questions during the live Q&A session.
So thanks a lot. So now is the question time. So are there any questions? You can also write the questions into the chat if you prefer. Okay, so at the moment I don't see anything, so let me ask first. So if I understood the results correctly, I mean, you are considering an arbitrary but finite arena, is that correct?
Oh, yes, we only consider finite arenas.
So is there any chance to extend these results to infinite arenas? Because I think what would necessarily be an issue here is, for example, the property of whether the game is finitely or infinitely branching and for which of the two players and so on. So have you been thinking about this?
So that's something we definitely want to investigate. But our proof technique for this paper is actually a proof by induction. And so by induction on the number of states and edges in arenas. And we do not know how to extend that in general to infinite arenas. So there is already a 1 to 2 player left for deterministic infinite arenas by Kolkomba and Nowinski for memoryless strategies and prefix independent objectives. And so at least in deterministic arenas, we think that it's possible to extend it to not necessarily prefix independent objectives and to the arena independent finite memory strategies. So we are working on that in deterministic arenas. About infinite stochastic arenas, I don't really know. I can't really comment on that.
Yeah, because if I remember correctly, I mean, the issues can be very tricky when the reachability objectives in these infinite arenas may require infinite memory and so on, and there are no optimal strategies and so on. So I would be interested to know whether something can be said about this. Okay, are there any other questions?
I think there's a question in the Q&A tab.
Q&A, that's right. So let me read the question. So is arena independence among finite arenas ever different from arena independence among countable arenas? So yeah, this is pretty much related to the previous question. So please.
So there's at least one example in which it is different, which is the mean payoff objective. So for the mean payoff objective, if you want to maximize for player 1 and minimize for player 2, in finite, deterministic, and stochastic arenas, pure memoryless strategies suffice. But in some strange infinite arenas, you can need infinite memory. So it's not always the case that when arena-independent finite memory strategies suffice in finite arenas, it suffices in infinite arenas. I think that will be the case for omega regular objectives, but not for general objectives such as a discounted sum or a mean payoff objectives.
Okay, so I hope that Stefan is happy with the answer. So anybody else? Okay, it's just thanks from Stefan. So this is nice. So let me thank you also. I mean, it was a nice talk.
Thank you very much.
Okay, so yeah, so I think we are ready to go on with the next talk. So, okay.
Hello, in this talk I'm going to present our recent work of Stackelberg Pareto synthesis. This is a joint work with Véronique Bruyère and Jean-François Raskin. I'll start by recalling the concept of reactive synthesis and the classical approach used to perform reactive synthesis using games. Then I'm going to introduce our new approach to reactive synthesis, which we call Stackelberg Pareto synthesis. Finally, I'll present some of the results we were able to obtain. Reactive synthesis deals with reactive systems, which are systems which constantly interact with the environment and must react to the events produced by that environment. The problem of reactive synthesis is stated as follows. Given a specification for the system, describing what the system should achieve, we want to synthesize an adequate controller for the system, describing how the system should behave, and we want to enforce the specification whatever the behavior of the environment. So no matter how the environment behaves and the event it produces, we want the specification to be satisfied. The classical approach for reactive synthesis in the context of game theory is to model the interaction using a two-player game in which player 0 represents the system and player 1 represents the environment. The specification corresponds to an objective in this game. I'll now recall a few concepts of game theory. So first, a game arena is a tuple G in which V and E correspond to a directed graph. V0 contains the vertices controlled by player 0, which are represented by circles in the game arena, and V1 contains the vertices controlled by player 1, which are represented by squares in the game arena. We consider plays, which are infinite paths starting with the initial vertex V0. Here, we have displayed a play row which starts in V0, goes to V2, and then loops infinitely often between V3 and V5. An objective omega I for player I is a subset of plays, and we say that the play row satisfies the objective omega I if row belongs to this subset of plays omega I. The reachability objective corresponds to the subset of plays which visit some set of vertices T. So for example, if the set of vertices T contains vertex V3, then our play row satisfies the reachability objective since it visits vertex V3. A strategy sigma I is a function which dictates the choices of player I during the play. Given the vertices which have already been encountered in the play, so H and the last vertex to be visited Vk, which belongs to player I, the strategy yields Vk plus 1, either from H and from Vk, and then we say that the strategy uses memory, or only from the last vertex to be encountered Vk, and then we say that the strategy does not use memory. We have represented here a memoryless strategy for player 0, which corresponds to selecting in the game arena and for each vertex of player 0, one single successor. We say that the play is consistent with strategy sigma I if Vk plus 1 is equal to sigma I of V0 to Vk whenever Vk belongs to player I. So this means that, in the play, whenever a vertex of player I is encountered, the next vertex to appear in the play is the one dictated by the strategy, given the vertices which have already been encountered. We can consider the set of plays which are consistent with a strategy. So for our example strategy sigma 0, we write plays of sigma 0, the plays which are consistent with strategy sigma 0, and in this case it contains 3 plays. The one which loops in V1, the one which loops in V4, and the one which loops in V7. Let's now come back to reactive synthesis. So the classical approach for reactive synthesis uses zero-sum games. That is,
the objective of the environment is the opposite objective of the system. For example, if the objective of the system is to reach some set of vertices T, then the objective of the environment is to avoid this set of vertices. We say that the environment is adversarial, meaning that it wants to make the system fail. And therefore, we want a winning strategy for the system. Here, we have represented every possible play in the game arena, starting from the initial vertex V0. Then, we can consider a strategy of player 0, which corresponds in this unfolding to selecting for each vertex of player 0 one single successor. The plays which are highlighted in blue are the plays which are consistent with the strategy of player 0. Since player 1 can play in such a way to obtain any of these plays in blue, we want player 0 to satisfy his objective in every plays which are consistent with his strategy. There are a few setbacks to this approach, namely that a fully adversarial environment is a bold abstraction of reality, as this assumes that the only goal of the environment is to make the system fail. But in practice, the environment is not composed of a single block and can be composed of one of several components, each with their own objective. One alternative to this is to consider the framework of Stackelberg games, which are non-zero-sum games, in which player 0 announces his strategy sigma 0, and then player 1 rationally answers with an optimal response with regards to his own objective. Therefore, the goal of player 0 is to announce a strategy which satisfies his own objective, whatever the rational response of player 1. So here we don't consider every response of player 1, but only the ones which we deem to be rational. I'll now introduce our new approach to reactive synthesis, which we call Stackelberg Pareto synthesis. I'll start by presenting our new model of Stackelberg Pareto games, sometimes written SP games for short. So a Stackelberg Pareto game consists in a game arena G, an objective omega 0 for player 0, who represents the system, and several objectives omega 1 to omega t for player 1, who represents the environment. These several objectives represent the components of the environment and their own individual objectives. We are again in the context of Stackelberg games, so player 0 announces his strategy sigma 0 and then player 1 answers with his own strategy. After responding with his strategy, player 1 receives a payoff in the corresponding outcome. So the payoff of a play row for player 1 is the vector of booleans, one for each of his objectives, such that in this vector there is a 1 at position I if and only if the objective omega I is satisfied in the play. Let's consider a simple example. So let's consider the case in which player 1 has 3 objectives, omega 1, omega 2, omega 3, and let's consider the play which starts in V0, goes to V2, and then loops between V3 and V5. The payoff of this play is the vector of booleans 0, 1, 0, as only objective omega 2 is satisfied and objectives omega 1 and omega 3 are not satisfied. Notice that when we discuss the payoff of a play, we only consider the objectives of player 1. We don't include the objective of player 0 when discussing the payoff of a play, and the reasons why will appear later. We can introduce a partial order on the payoffs. So for example, the payoff 0, 1, 0 is strictly smaller than payoff 0, 1, 1. Intuitively, this can be understood as player 1 preferring some payoffs to others. So for example, he would much prefer to obtain this payoff than this payoff, as they both satisfy objective omega 2, but as this one also satisfies objective omega 3. Again, we are in the context of Stackelberg games, in which player 0 announces his strategy sigma 0, and then player 1 answers with his own strategy. So after announcing his strategy sigma 0, player 1 can consider the set of plays which are consistent with this strategy, which we have represented here, and he can consider the corresponding set of payoffs. So each play has its own payoff, and it can be the case that different plays have the same payoffs. Then, since player 1 is rational, it is natural that he would want payoffs which are maximal with regards to the partial order which we have introduced. These payoffs which are maximal are the Pareto optimal payoffs. So in this case, they are highlighted in blue given the plays which are consistent with the strategy announced by player 0. We can see that this payoff is not Pareto optimal as it is strictly smaller than this one, and we can see that these two payoffs are not comparable given our partial order. So we write the set of Pareto optimal payoffs P of sigma 0. In this case, it contains the two payoffs 0, 1, 1 and 1, 0, 0. we can finally introduce our new approach to synthesis, which we call Stackelberg Pareto synthesis. The Stackelberg Pareto synthesis problem, SPS problem, is to decide whether there exists a strategy sigma 0 for player 0, such that for every play which is consistent with this strategy and which has a Pareto optimal payoff, it holds that the play satisfies the objective of player 0. We assume that the environment is rational and will respond to the strategy announced by player 0 in such a way to obtain a Pareto optimal payoff. Therefore, it is sound to ask that player 0 satisfies his objective omega 0 in every such rational response. Here we consider every play which are consistent with the strategy announced by player 0, and we can consider their payoffs. For every play which has a Pareto optimal payoff, we want player 0 to satisfy his objective omega 0, and for a play which does not have a Pareto optimal payoff, we don't care whether or not player 0 satisfies his objective. This is because, since player 1 is rational, he will play in such a way to obtain one of these payoffs, so he will play in such a way to obtain one of these plays, and will not play in such a way to obtain this play. Let's now consider an example of this problem. So let's consider this game arena, in which I have highlighted the payoff of a play next to the vertex in which it eventually loops. I have also specified whether or not player 0 satisfies his objective in this play. Let's consider the strategy sigma 0, such that from vertex v3, player 0 always decides to go to v5. We can consider the plays which are consistent with this strategy sigma 0, namely the play which loops in v1, the one which loops in v4, the one which loops several times between v3 and v5 and ends up in v6, and the one which loops infinitely between v3 and v5. We can consider the payoff of each of these plays. So this play has payoff 0, 0, 1, this play has payoff 1, 0, 0, this one has payoff 0, 1, 1, and this one has payoff 0, 1, 0. We can identify the payoffs which are Pareto optimal, given the ones allowed by strategy sigma 0. So these Pareto optimal payoffs are 1, 0, 0 and 0, 1, 1. We can see that strategy sigma 0 is not a solution to the SPS problem, as there exists a play, namely v0, v2, and which loops in v4, which has a Pareto optimal payoff, 1, 0, 0, which appears in the set of Pareto optimal payoffs, and which does not satisfy the objective of player 0. The only other memoryless strategy is not a solution either to the problem. However, we can consider the finite memory strategy, sigma 0 prime, such that sigma 0 prime goes from v3 to v5, and if v3 is encountered a second time, goes to v7. It can be shown that sigma 0 prime is a solution to the Stackelberg Pareto synthesis problem, as every play with a Pareto optimal payoff satisfies the objective of player 0. In fact, in this case, the Pareto optimal payoffs are 0, 1, 1 and 1, 1, 0, and every play with such a payoff satisfies the objective of player 0. This shows that player 0 may need memory in order to have a solution to the Stackelberg Pareto synthesis problem. In the following, we consider Stackelberg Pareto games, in which every objective is a parity objective, which we call Parity Stackelberg Pareto games. These model the general class of omega regular objectives. We have also considered the case in which every objective is a reachability objective, which we call Reachability Stackelberg Pareto games, which is a simpler setting. Let's now present some of the results we were able to obtain. First, we have shown that the Stackelberg Pareto synthesis problem is next time complete for reachability SP games and for parity SP games. This is an interesting result for a natural class of games played on graphs. Then, we have studied the fixed parameter complexity of the Stackelberg Pareto synthesis problem. We have found that solving the SPS problem is fixed parameter tractable for reachability SP games for parameter t, which corresponds to the number of objectives of player 1, and fixed parameter tractable for parity SP games for parameters t and the maximal priority according to each parity objective of player 1. This is sound, as in practice we can assume those parameters to have small values. It should be noted that our next time algorithm is not fixed parameter tractable, and that our fixed parameter tractable algorithm is not usable to show the membership to next time, as its time complexity is too high. I'll now try to give the intuition for the next time membership result. We use an important result on the strategies which are solution to the problem, namely that if player 0 has a solution to the problem, then he has one which uses finite memory with at most an exponential number of memory states. We can then devise a next time algorithm in which we non-deterministically guess such a strategy, which we can assume to have an exponential size. Then we check that it is indeed a solution in exponential time using automata techniques. I'll now try to give the intuition of why finite memory strategies with an exponential size are sufficient. So we start from a solution sigma 0 to the Stackelberg Pareto synthesis problem, and one play rho I per Pareto optimal payoff. So for each of the Pareto optimal payoffs, we identify one play which realizes that payoff. In this case, there are 4 payoffs, so there are 4 such plays. Then we create a strategy sigma 0 hat, which follows sigma 0 in the prefix of these plays. So as long as we follow one of these plays, we play the same way as in sigma 0, and then as soon as a deviation occurs, so as soon as player 1 decides to go outside one of these plays, we switch to a so-called punishing strategy, which imposes that every resulting play either satisfies the objective of player 0 or does not yield a Pareto optimal payoff. This makes the deviation for player 1 irrational. Then we decompose each of these plays rho I into at most exponentially many parts and compact them. We can see that the resulting strategy sigma 0 tilde has an exponential part yielding a compacted version of these plays and an exponential part which deals with the punishing strategies. Overall, this strategy has an exponential size. We now consider the simple setting of 3 arenas, which are trees with loops on the leaves, and we have shown that in this simple setting and for reachability Stackelberg Pareto games, the Stackelberg Pareto synthesis problem is NP complete. We have shown the NP-hardness using the set cover problem, which is also NP complete. I'll now recall this set cover problem. So we have a set of n elements, we have m subsets of elements, we have an integer k, and the goal is to find k indexes such that the union of the corresponding sets completely covers the set of elements. The goal is to devise a reachability Stackelberg Pareto game such that player 0 has a solution to the SPS problem in this game if and only if there exists a solution to the set cover problem. Let's consider this simple instance of the set cover problem in which there are 3 elements to cover, 3 sets to cover these elements, and we want to find 2 out of those 3 sets in order to cover the elements. This is the arena of the corresponding reachability Stackelberg Pareto game. So we can see that this is a tree arena as it's a tree with loops on the leaves. We can see that there is one specific payoff for each of the elements we aim to cover. So element 1 has the specific payoff 0, 1, 0, 0, element 2 has 0, 0, 1, 0, and element 3 has 0, 0, 0, 1. We can also see that for each of the sets, there is also one specific payoff. So since set S1 contains element 1 and element 3, its payoff is 1, 1, 0, 1. This part of the payoff in red is devised in such a way that it is strictly larger than the payoff for element 1 and strictly larger than the payoff for element 3. We can also see that in this arena, there is only 2 vertices where player 0 can make a choice, vertex C1 and vertex C2. These vertices correspond to the choices that can be made in the set cover problem in order to cover the elements. In these vertices, player 0 can select one of the sets. None of the plays in G1 satisfy the objective of player 0, and every play in G2 satisfies the objective of player 0. Every play in G1 is consistent with any strategy of player 0. This is simple to see since, from the initial vertex V0, player 1 can play in such a way to obtain any of these plays without any input from player 0. Since these plays also don't satisfy the objective of player 0, it must be the case that, in a solution, the payoff of these plays are not Pareto optimal. If that were the case, it would mean that there exists a play with a Pareto optimal payoff, which also does not satisfy the objective of player 0. Each payoff in G1 must therefore be strictly smaller than some payoff in G2. which corresponds to a set. So I have highlighted here in bold a strategy for player 0, which is a solution to the Stackelberg Pareto synthesis problem in this game. Let's consider the plays which are consistent with this strategy. So there are those 3 plays here and their corresponding payoffs. There is this play here, which corresponds to selecting set S1, and this play here, which corresponds to selecting set S2. We can see that this payoff is strictly larger than this one and this one, and we can see that this payoff is strictly larger than this one. Therefore, when we consider the Pareto optimal payoffs, they are only realized by plays in G2. And since every play in G2 satisfies the objective of player 0, it means that this strategy sigma 0 is a solution to the Stackelberg Pareto synthesis problem. This corresponds in the set cover problem to selecting set S1 and S2 in order to cover these 3 elements, which we can see is a solution to this problem. Let's now turn to the next time hardness of the Stackelberg Pareto synthesis problem. In order to show this result, we use a succinct variant of the set cover problem, which we have shown to be next time complete. This corresponds to the set cover problem succinctly defined using CNF formulas. We can see that the game arena of the corresponding Stackelberg Pareto game is much more complicated, but the arguments that we used are similar to the ones that we used for the NP hardness on 3 arenas. Finally, to show our fixed parameter tractability results, we provide a reduction from our Stackelberg Pareto game to a challenger-prover game, which is a 2-player zero-sum game played between player challenger and player prover. This game is devised in such a way that there exists a solution to the Stackelberg Pareto synthesis problem in the original game, if and only if prover has a winning strategy in the 2-player zero-sum challenger-prover game. The objectives in this game are described in a generic way and later adapted to parity and reachability. The intuition behind this game is that prover tries to show the existence of a solution and challenger tries to disprove it. Thank you for your attention, and I'm looking forward to your questions.
Okay, thanks a lot. So Clement is with us. So please, if you have any questions, then indicate that somehow, or you can put them into the chat or into the Q&A window. Okay, Danielle, please.
Yes. So I just a technical question, because maybe I missed something in the talk, but why is it important that the objectives for the player 1, say, are vectors of booleans? Cannot you just have any finite partial order? I mean, what does it change?
Well, in this case, we considered games in which every objective is either a parity objective or a reachability objective, and therefore what we encode using the payoffs is whether or not this objective is satisfied. So this is why we have vectors of booleans, and then the order which we have used is the natural order, not lexicographic, but the natural order which you can use on vectors of booleans. And we are currently trying to extend this to quantitative objectives, in which the vectors would then be vectors of any value between some range. And this is a more complicated problem, both in the way to define the problem and in the way to show the results.
Okay, so I missed that. Thank you.
Okay, anything else? So if not, then I have a question. Actually, I intended to ask you about the quantitative objectives, but this is what you've already answered in between. But I would also be interested to know whether this is applicable to stochastic games, because you have just, deterministic games.
I don't really have an answer for this. We don't have any results on that. We have not checked that out yet. We have just considered the current setting, which is either all reachability or all parity objectives. We are now considering vectors of different objectives. So in which you can have a different prefix independent objectives. So for example, one Rabin objective and one parity, and then one street objective, and so on. And as I said, qualitative objectives, but we have not looked at the setting of stochastic games.
Okay, and I have another question related to these quantitative objectives, because there, I mean, the player zero doesn't have just winning or losing strategy. I mean, he can, the question is whether he has an optimal strategy. So do you think that you can give a kind of generic result saying under what condition, or maybe always, player zero has an optimal strategy which achieves the best quantitative value? Or do you think that is that the optimal strategy doesn't exist?
Well, we don't actually have any results on quantitative on the quantitative setting yet. So I don't really have an answer for this yet. We're working on it.
There's an interesting open problem in the area of so-called security or patrolling games, where the Stackelberg equilibrium is used as a solution concept. It is known that the leader has an optimal strategy, but it is not yet known whether he also has a finite memory optimal strategy. Although the soup over all finite memory strategies is the same as the soup over all strategies. So yeah, so if you have some insights in the future, this might be very, very interesting. I mean,
definitely.
Okay, so thanks a lot.
Thank
so
you.
The last opportunity for extra additional questions. Well, I don't see any, so let me thank you for this wonderful talk.
Thank you very much.
Before the end of the session, I was asked to remind you that tomorrow evening there will be a presentation of the Conquest 2022, so for the next conference. Okay, so I hope to see you there. And well, that will be the end of the session. So thanks a lot to all our speakers, and thanks a lot to you for being with us and for participating in this session. So thanks and goodbye.